Welcome to the UGC lecture series. This is the EPG Pathashala lecture series on machine learning, and in this module and the ensuing modules we are going to look at a very important concept of machine learning today, which is based on the Bayes principles. So, in this we give a brief introduction to the general approach of Bayes learning, and we will keep on talking a little bit about a famous person called Bayes and his theorem, because most of Bayes probabilistic learning, as it is called in machine learning, is based on Bayes theorem. So, this module concentrates on the use of probability for machine learning, basically the basics of that. So, these are the people responsible for the creation of this particular module. So, let us look at the learning objectives of this particular module. We are going to look at understand probability. We had actually spoken about probability and Bayes theorem in the beginning of the machine learning paper, where we gave some basics, but here we are going to connect it with learning. So, we are here to understand probability, Bayes theorem and Bayes learning, and we will understand the Bayes learning framework basically, and then we will understand probabilistic classification. We take a simple example and see how probability is used in a very important problem of machine learning, classification. The key terms here are Bayes theorem, Bayes learning and classification. So, let us look at the key problems that we want to solve. So, how do you fit a model to data? We have lots of available data. How do we fit a model to this data? This is a question we want to answer. So, how do you choose weights and thresholds for this model? Any model, there will be some weights associated, there will be some threshold. How do we choose this? Then, how do you incorporate prior knowledge? So, in order to model something, you need to have some prior knowledge. How do you incorporate prior knowledge? Then, how do you merge multiple sources of information? You have different sources of information, how do you merge them? And how do you model uncertainty? All information is not certain. So, how do you model uncertainty? So, this is the key problems that you have to address when you are trying to fit a model to a data. And as you can see, fitting model to data is the essence of machine learning today, not rules, because today you have data in abundance. So, fitting models to data is very important, and fitting models to different types and modes of data is becoming more and more important. So, for all this, these are some of the fundamental questions that you have to answer. Now, for all these questions, Bayes learning or reasoning provides solutions. So, that is why we are going for Bayes reasoning or learning, as it is called. Okay. So, what is Bayes reasoning? Bayesian reasoning, as it is called. It is nothing but probability, statistics and data fitting. And for example, here you have some data, you are trying to fit a model. Here you have some data, you are trying to fit a curve. So, frequentist statistics or orthodox statistics, you have probability defined as a frequency of occurrences in an infinite number of trials. So, you take a large number of trials and find out how many were of correct, let us say Boolean, correct and wrong, and so based on that you will say that okay, most probably this is correct if 90% is correct. But that is called frequentist statistics or orthodox statistics. This is probability, statistics and data fitting. Now, that is the initial part of Bayes. We will go further as we go along. Now, we are going to look at some principles of probability theory. So, probability theory, as told by Pierre Simon Laplace in long back in 1814, is probability theory is nothing more than common sense reduced to calculation. So, he says that probability theory is actually common sense, but it is given in a calculatable way. That is what he says. This was told by Laplace way back in 1814. So, we are going to look at some principles that we are going to use. So, what are the probability basics? Prior, conditional and joint probability of random variables. So, you have a large number of random variables. You are going to talk about prior probability of a variable, conditional probability of a variable and joint probability of more than one variable. So, first let us look at prior probability. This is given as P of x, or the probability, prior probability of x. What is the probability that x has happened before? Then conditional probability is given that x2 has occurred, what is the probability of x1, or given that x1 has occurred, what is the probability of x2. So, that is conditional probability. Now, you have joint probability. What is the probability of x1 and x2 occurring? This can be told as where x is defined in terms of x1 and x2. So, what is the probability of x is nothing but the probability of x1 and x2 occurring. Then you have a relationship between the probability of that joint probability that says that probability of x1 and x2 occurring is nothing but the probability of x1 occurring, and given x1 is occurring, what is the probability of x2 occurring, or it can be told the other way around also, probability of x2 occurring and what is the probability of x1 occurring given that x2 has occurred. Now, if x1 and x2 are independent variables, then probability of x2 given x1 is nothing but the probability of x2, because x1 does not affect x2. Similarly, probability of x1 given x2 is nothing but probability of x1, because x2 does not affect x1. x2 having occurred does not affect x1. And similarly, probability of the joint probability of x1 and x2 now reduces to probability of x1 into probability of x2. So, these are some of the probability theorems as they are called in reference to what we need for machine learning or Bayesian learning. The Bayesian rule. This is we have seen this a lot, we have concentrated on this in the previous initial modules also, but let us revisit it because this is a very important, this will be keeping on being spoken about as we go along in machine learning. So, this is nothing but given what is the probability of C given x, you can think of C as a class. So, given the data, what is the probability of a class can be written as probability of given the class, what is the probability of the data occurring into the prior probability of the class divided by the probability of the data. So, this is called as in terms of probability as being called as posterior probability into likelihood is equal to likelihood into prior by evidence. So, this is the famous Bayes rule which we will be using again and again: posterior probability, likelihood, prior probability and evidential probability. This evidence we will see more in detail about this. So, this is one formula that we need to, or one theorem that we need to keep in mind and almost know it from in our sleep, because the whole of Bayes or probabilistic learning is based on Bayes theorem. Okay. So, the Bayes theorem states that given x, what is the probability of C can be found out by given the prior probability C, given the likelihood, that is given the class C, what is the probability of x is called the likelihood data, and the probability of divided by the probability of the data. Now, this is the famous Bayes theorem again told in some other words. So, this is the joint probability, this is the conditional probability, this is the posterior probability of weight vector W. This we are talking in terms of a weight vector, posterior probability of weight vector W given the training data D. So, remember we said we wanted to find out some weight, prior probability of weight vector W, the likelihood or probability of observed data given that the weight is W, the probability of the D, that is the training data, what is the probability of that particular training data. This is given by this. So, there are discrete and continuous variables. How do we model the world? So, discrete variables, probabilities can be over discrete variables. So, in which case it is just count. So, heads and tails. So, if you have PC is equal to heads is 0.5, PC is equal to tails is equal to 0.5, count of heads plus count of tails is equal to 1. So, the probability is always 1. This is a simple toss of a coin example where we have two coins, the coin tossed and you have heads and tails. So, this is probabilities over discrete variables. Now, if it is only discrete variables, then it is not so interesting. So, we talk about continuous variables. So, in continuous variables what we talk about is how do you describe beliefs over x, where x is a phase or a joint angles or something like that. It is a real number. So, probability distribution function is what is used. This is called as marginal probability. So, instead of using counts, we use a probability distribution function. So, if it is discrete, we use count or frequency, and if it is continuous, we use a probability distribution function called as PDF. So, for example, this is a probability x is probability this function or this distribution is called as PDF. And now we have an interesting property that we normally assume a Gaussian distribution which has its own parameters, a mu, a mean and a standard deviation sigma. This we will again talk about a little more in detail as we go along. Okay. Now, the question is why do we, so this the probability distribution data, almost all data we assume that the probability distribution function is Gaussian. Okay. So, again I will repeat what is, where did we come to this? We said that probability, to find probability of a random variable, you for discrete case you just count large number, but you have to count. For continuous variables you cannot count. So, we normally use a probability distribution function, and we assume that data normally follows normal or Gaussian distribution, which has its own mean and standard deviation. So, why do we use this Gaussian distribution is the next question. It is convenient for analytic purposes, it follows a central limit theorem, it works well, it is not for everything, but it is a good building block. So, that is the Gaussian distribution, and the Gaussian distribution, there is a formula associated. So, a function of x is equal to 1 by sigma root 2 pi into e to the power of half x minus mu by sigma the whole square. This is a typical mathematical definition of a Gaussian function. So, we are just defining a Gaussian function, and that diagram there shows you the Gaussian distribution, how it follows. It is centered around mu and it is distributed along sigma. Okay. So, this Gaussian distribution function is what we will assume for our data. Now, but assuming a distribution shape is one thing, but assuming the parameters of the distribution, which is your mu and sigma, is where the challenge lies. So, what we are trying to do is, we assume the data is fitting Gaussian, but once we assume that, we have to find the different values of mu and sigma. That is the basis. Okay. This is a bell shaped curve with different centers and spreads depending upon the value of mu and sigma. Mu will decide the center and sigma will decide the spread or the variation. Okay. Now, we will talk about inference. So, we have spoken about probability, we have spoken about probability, typical definitions of probability, we spoke about different angles, we spoke about Bayesian rule, then we spoke about how do we determine probability for from data for discrete and continuous cases. Then we spoke about Gaussian distribution, and we spoke about how to the parameters of the Gaussian distribution. Now, we will go to inference. So, how do we reason about the world from observations? Three important sets of variables are available. One is the observations, what have you observed? Then there are some unknowns, and there are some auxiliary or nuisance variables. So, there are three types of variables: observations, unknowns and auxiliary variables. So, given the observation, we have to find the probabilities of the unknown. That is what we talk about as inference. Now, let us talk about parameter estimation. Okay. So, problem, given lots of data, we have to determine the unknown parameters. That is our job. So, there are various estimators available: maximum a posterior, that is MAP, maximum likelihood, ML, unbiased estimators, and there is a problem associated with parameter estimation, which is overfitting. A model that fits the data exactly will not generalize. So, it is not good. This we have seen before also, overfitting is not good, and occurs when an estimate is obtained from a too much spread out posterior. So, if you have like that, then what will happen is you will try to fit the data exactly and you will come across as overfitting. So, how do we estimate the parameters is what we are going to, is the basis of again Bayes learning. Now, let us relook at the probability principles once more before we go further. So, probability theory is common sense reduced to calculation, that is what Laplace said. Then given a model, we can derive any probability. So, that is the next one. Describe the, now for given the model we can determine the probability, but how do we determine the model? The model of the world is described, and then compute the probabilities of the unknowns using Bayes rule. So, using calculate posterior given likelihood and evidence and prior. Okay. And parameter estimation you have to do very carefully, because it leads to overfitting when the posterior is in peak. So, but it is easier for Bayes prediction, we will come to see that. And least square estimation is a special case of MAP, that is maximum a priori posterior probability, and can suffer from both overfitting and underfitting. We will see what this least square estimation is as we go along. And you can learn or marginalize out. After you learn the parameters, you can marginalize out all the parameters. So, this is the principles of probability that we use for Bayesian learning. This is defined in terms of the learning principle. Now, what are the benefits of the Bayesian approach? That is the next question we have to ask. So, principal modeling of noise and uncertainty, uniform learning for both learning and synthesis. You can learn all the parameters and so these are the benefits, good results from simple models, and lots of good research and algorithms has been done using Bayesian. Okay. Now let us look at some applications. It is used in data mining, it is used in robotics, it is used in signal processing, it is used in bioinformatics, it is used in text analysis, for example in spam filters, and it is used in graphics. So you see that no area of machine learning application has been left. So Bayesian has been used everywhere. We have just taken overall applications, data mining for all types of scenarios, robotics, signal processing for all types of scenarios, could be music, could be video, could be audio, it could be anything, speech, bioinformatics, text analytics and all spam filter, not only spam filters, it could be used for information retrieval, search engine ranking, could be used for a lot of things. Graphics nowadays it is being used a lot, visualization and so on. Okay. So now let us look at the Bayesian framework. Now allows us to combine observed data and prior knowledge. So observed data is available and prior knowledge is available. The framework allows you to combine both. Okay, remember it's based on Bayes theorem. Provides practical learning algorithms. Algorithms are provided, there is available algorithms. It is a generative method, that is it is a model based method which offers a useful conceptual framework. The Bayesian framework assume that we always have a prior distribution for everything. Okay, we always assume there is a prior distribution for everything, and the prior may be very vague. When we see some data, we combine our prior distribution with a likelihood term to get a posterior distribution. Remember, this is got from the Bayesian theorem. The likelihood term takes into account how probable the observed data is given the parameters of the model. So that is the job or the role of the likelihood term, and it favors parameter settings that makes the data most likely. It fights the prior, because if you have done it as only according to prior, you are not considering the observations that you have seen. With enough data, likelihood has more weightage than the prior. Okay. So what is Bayes learning now? Bayes learning uses probability to model the data and quantify uncertainty of predictions. It facilitates incorporation of prior knowledge. It allows for decision theoretic reasoning. Probabilistic, it has a probabilistic approach to inference, and there are some assumptions. The quantity of interest, that whatever you are modeling, is based on a probability distribution. If you did not assume that, you cannot do Bayesian learning. And the optimal decisions are decisions about probability and observations. And it provides a quantitative approach to weigh how evidence supports alternative hypothesis. So how the evidence supports alternative hypothesis. It gives you an actual quantitative approach. We will see this. Now some of the features of Bayesian learning are each observed training data can incrementally decrease or increase the estimated probability of a hypothesis. This hypothesis is what is the final finding that you have done. Rather than completely eliminating a hypothesis if it is found inconsistent with a single sample, we can incrementally increase or decrease the estimated probability. We are not going to eliminate anything. And prior knowledge can be combined with observed data. Observed data is used to find the likelihood, determine the final probability of a hypothesis. New instances can be classified by combining prediction of multiple hypotheses, and even in computationally intractable cases, Bayesian optimal classifier provides a standard optimal decision against which other practical models can be compared. Before I go on further, what is this hypothesis? This hypothesis is trying to find the probability of something based on posterior probability, let us assume, based on class based on data. That is the hypothesis, which is the class. Now the class will be associated with the probability, okay, and so it is not eliminated. Some of the class is not eliminated, that is one thing. Next is the prior probability also plays a role in determining the probability of the hypothesis. New instances can be classified by combining predictions of multiple hypotheses, and even if it is computationally intractable cases, Bayesian optimal classifier produces a standard optimal decision. So Bayesian decision theory come long before version spaces, decision tree learning and neural networks came into the picture. It was studied more in the field of statistical theory and more specifically in the field of pattern recognition. Before machine learning came into the picture, Pattern recognition was an old school of thought, and there Bayesian decision theory came into the picture. Bayesian decision theory is at the basis of important learning schemes such as naive Bayes classifier, Bayesian belief network and expectation maximization algorithm, which we will be seeing as we go along. The next module is about naive Bayes classifier, then we will have 2 modules on Bayes belief networks, and we have on expectation maximization also. And Bayesian decision theory is also useful as it provides a framework with which many non-Bayesian classifiers can be studied. And so the advantages are Bayesian approaches including naive Bayes are among the most common and practical ones used in machine learning. Bayesian decision theory allows to revise probability based on new evidence. That is very important. As new evidence comes in, you can revise the probabilities. And Bayesian methods provide a useful perspective of understanding many learning algorithms that do not manipulate probabilities. It helps you to understand. Now, let us just relook at the Bayes theorem from the hypothesis viewpoint. Now, look at this. Just assume D is the data samples and H is the hypothesis. So, given the probability of what the hypothesis given the data samples can be found out by the likelihood of the data given the hypothesis into the probability of the hypothesis divided by the evidence of the data. So, this is the goal is to determine the most probable hypothesis given the data plus any initial knowledge about the prior probabilities of the various hypotheses that are available in H. That is the total set. The prior probability of H reflects any background knowledge we have about a chance that H is a correct hypothesis before having observed the data. You have not seen any data, but we know that these classes are very common like that. Prior probability of D, that is P of D, it reflects the probability that the training data D will be observed given no knowledge on which the hypothesis holds, that we do not know. And conditional probability of observation P D comma H, or it is called likelihood also, denotes the probability of observing data D given that the hypothesis is H. So, the posterior probability, the final thing that we want to find, given the data what is the hypothesis, it represents the probability that the hypothesis holds given the observed training data. It reflects our confidence that H holds after we have seen the training data D, and it quantifies that machine learning researchers are interested in. It is a quantity. Bayes theorem allows us to compute this posterior probability. Okay. Now, let us look at maximum a posteriori and maximum likelihood called as MAP and ML. So, it is to find the most probable hypothesis H from a set of candidate hypothesis H given the observed data D. Okay. So, map of hypothesis H of map, I will just explain this a little more in detail. This gives, you have, let us assume in your H space, capital H set, you have a set of hypothesis small h, and what you do is you try to find the hypothesis that gives you the maximum probability for the given data. So, for the given data you find the likelihood and you find the prior probability and you find the probability of the hypothesis. The probability of the hypothesis does not change, the probability of the data does not change whatever the hypothesis. So, you can remove that. So, you just take the argument max. What this argument max is telling you is find the hypothesis that maximizes the likelihood into prior probabilities. That will give you the, or maximizes, in other words, maximizes the probability, posterior probability. That hypothesis is the hypothesis that you have to find. That is the meaning of maximum a priori. Now, if every hypothesis in H is equally likely, that is we do not need to multiply it by P of H because probability is equal, then that is not going to affect your posterior, in which case you have only likelihood of the data. Find out whichever gives you the maximum likelihood of the data. So, that becomes maximum likelihood. So, when posterior all hypotheses are equally likely, then the posterior probability reduces to likelihood. So, the example of this is we have data on past student performance. For each student we know that the student's GPA is greater than G. If a student has a strong maths M, if a student is a hard worker H. If student passed or failed course, a new student comes along with value G equal to G, M equal to M and H equal to H. We want to know if they are likely to pass or fail that course. So, we want to find out this. So, this can be done by using a classifier for using the posterior. So, this is a general Bayes example. So, you have here the GPS, you have the maths, and then you have the performance and the pass or a fail and the probabilities. So, with that you can assume P of pass is equal to 0.5, P of fail is equal to 0.5 because it is equal probable. Then you are given these values. So, with these values you can find that the probability is 0.25, and joint probability distribution grow exponentially with the number of features. So, for binary valued features we need approximately 2 to the power of p joint probability distribution for each class. Now, why should we use probability Bayesian classification? It is because we can calculate explicit probabilities for the hypothesis among the most practical approaches to certain types of learning problems, and each training sample can affect or incrementally increase or decrease the probability of a hypothesis. So, prior knowledge can be combined, we have discussed this, predict multiple hypotheses weighted by the probabilities, and even when Bayesian methods are computationally intractable, they can provide an optimal decision. So, now we will talk a little bit about the use of Bayes for an optimal classifier. We will go in detail in the next module. So, one great advantage of Bayesian decision theory is that it gives us a lower bound on the classification error that can be obtained for a given problem. So, the most probable classification of a new substance is obtained by combining the predictions of the hypothesis weighted by the posterior probabilities. So, you can find out that you can take all the hypotheses and find this out, where V is the set of all values of a classification and Vj is one possible such classification. Unfortunately, Bayes optimal classifier is too costly to apply, therefore, we will apply naive Bayes classifier. So, you can weight it and do it, but there is a problem with this because it is too costly. So, we will go for naive Bayes. We will consider this in the next module. Now, before we conclude this module, let us talk about the different things, conceptually the different aspects that Bayes learning can be used for. So, we said that Bayes optimal classifier is too costly to apply. Naive Bayes uses conditional independent assumptions to set up the, to reduce the cost, but in many cases this is too restrictive. Therefore, there is the Bayes belief networks came into the picture. It is an intermediate between optimal classifier and naive Bayes classifier, because it allows stating conditional independence assumption that apply to subsets of the variables rather than single variables. So, it is actually between Bayesian optimal classifier and naive Bayes classifier. Then the other aspect that we will be considering is the expectation maximization algorithm. Here we consider naive Bayes classifier using unlabeled data. Till now whatever data we had was labeled, it was supervised learning. So, how can we estimate this, a probability of A given C? So, what we do is we randomly assign numbers to P of C. What is P of C? P of C is the prior, P of A comma C is the probabilities. So, what we do is we compute, we are given probability of A given C and probability of B given C. We so randomly assign, then you compute the value, recompute the maximum likelihood and calculate the log likelihood. You keep on doing this until the likelihood of the data improves. If it is not improving, you stop. So, whatever you have got is the data. So, here we have unlabeled data. We start with random probabilities and recompute. We will go into detail about this expectation maximization as we go further. Now, in this module, we have explained probability, Bayes theorem and Bayes learning. We discussed the Bayes learning framework in general. We explained maximum A posteriori and maximum likelihood called as MAP and ML. With that, we will stop this module.